So my name is Jean-Paul Smets. I'm a CEO of a small software company in Europe, and I'm going to introduce a new big data open source project named Vendelin. So the agenda of my talk is first to tell you a bit about our background. We are publishers of open source ERP called ERP5, and after that I'll introduce the toolkit that we are creating and that we call Vendelin Exanalytics. Our goal is to manage exabytes of data within 10 years. And the challenge we have to solve is something that people call out-of-core algorithms. So let's see our background. So 10 years ago, I decided to write something like SAP, but in open source. Actually, it's even more than 10 years ago. And now we have it. It's deployed in banks, in very big companies. So first, we started with MySQL. Now we use MariaDB for more than 3 years. And around that, we added a layer of distributed object storage called NEO. And that layer was made with the same language as the language we use for programming, that is Python. So NEO provides us very fine-grained security, kind of security or access rules you don't even find in Oracle application. It provides full traceability of every change by any user at any time. So if somebody writes something in the system, then changes it, we can still find the previous value. And it's quite scalable. And Python allows us to change the code of the system while the system is running. With this, we can do 24/7 hours running system, which code can evolve anytime without having to recompile anything. Then we wrote the ERP that provides the supply chain, the finance, the MRP. It has web, workflows, to-do list, notification, human resource, task management, payroll, CRM, document management, quite big. And at the end, we sell customizations for different industries, like banking, aerospace, health, chemical, government, NGOs. That's the business. We are present everywhere except in the United States. So France, Germany, Japan, China, Africa, Brazil, but not in the United States directly. So one of our customers is Airbus Defence and Space, and the ERP is used to manage every purchase of satellite images from this satellite called TerraSat X. It's a German satellite managed by the German Space Agency that can see through the clouds. It can even see through the roof of houses if the roof is thin enough. Yeah.
No.
Yes. It's X-band satellites. It works a bit like a radar or like a scanner. It sends it lightens from the sky, then the reflection goes back, and it can see through the cloud and through thin layers. Wow. It's very useful, for example. Sorry? It's pretty useful because when there were, for example, floods in China a couple of years ago, it was quite cloudy. But to help people save citizens which house was flooded, being able to see through the clouds is pretty useful because then you can recognize which area has been destroyed. So it also has very nice aspects. So this satellite needed a system that has many complex or traceability features. It's being audited by the German Security Agency every month, I think. And so they had no choice than use ERP5 open source ERP. And another customer that's interesting, they use the same software actually in Oregon for something called the Miles Tax, and in Dublin, and in France, and I forgot which, yes, in UK also. And nowadays, with ERP5 on top of MariaDB, we can generate 51,000 invoices per hour with quite complex workflows that generate many taxes, that has many steps. So we often hear every year in reports about open source, when you ask like Standard & Poor's 100 companies, would you use open source for your main enterprise resource planning software application? And they say, no, it's too early, it's impossible. It's been 10 years, we hear every year the same thing. But these values, like manage 120,000 new customers per year for, let's say, for a French company, multiply by 5 for US, 51,000 invoice per hour, or 7 billion contacts managed per year, that's quite significant. This is not small business ERP, it's really big company ERP. And the message is that nowadays, yes, it's possible to run a big company ERP based on MariaDB, and even a central bank, even a drug company in Japan, with strong transactional requirements. There's no issue for doing that. And this is actually what we live from. And doing it with open source is so much more flexible and cheaper that we have lots of time for lots of research and development. And let's now discuss this research and development. So a few months ago, we thought, what is all this fuss about big data? That sounds like the new buzzword to collect money from government and customers. Is it serious or not? Okay. Well, anyway, if there's money to collect, it can finance R&D, so it shouldn't be that bad. Yet, we'd like to know if there's anything serious behind. So, we studied a bit and found that one of the best machine learning toolkit is called Scikit-learn, and is used actually by Google for their proof of concept quite often, by Evernote, by Spotify, by actually quite many web companies. Are you aware of what is machine learning? Who knows? Okay, good. So, just to give you an idea how far it is nowadays, if you put like an electroencephalogram on your head and take all the signals, put the signals in a database, then ask someone, please think very seriously a letter of the alphabet, like D, then electro, D, electricity signal recorded in the database. Then you repeat the same operation for every letter in the alphabet. Then, for example, 100 people, and you collect a large sample of people thinking of a letter in the alphabet. Then you apply some statistics, that means some type of mathematics. Take a random person who was not part of the previous sample, put him the electroencephalogram on the head and tell him, think strong about a letter in the alphabet. And he will think, for example, P. Then P will appear on the computer screen. Just by comparing the signals, the electric signals generated by the brain through the encephalogram, just by mathematics, pure statistics, no kind of a computer being able to understand people, just mathematics. Think a letter, the letter appears on the computer screen. So this was not possible 20 years ago. At that time, statistical science was not that developed as it is today, and lots of mathematicians have really changed the nature of algorithms that are used for statistics and machine learning to the point that computer nowadays can guess nearly what you think. So, once you understand this, you understand that the key for machine learning and for big data is mathematics. Where do we find great mathematicians in the world? There is something called Fields Medal, it's like the Nobel Prize. So, there are 11 Fields Medal in US, 10 in France, 9 in Soviet Union, 6 in United Kingdom, 3 in Japan, etc. And there is one that is not listed here. It's Alexander Grothendieck. He's like a French who decided that nationality should not exist, and he abandoned any nationality, so he's not in the statistics. And the issue with those mathematicians nowadays is that they are very well paid, like 7-digit salaries in the United States. So you can forget the United States for mathematicians. They are all hired already by Google, Facebook, and so on. So the only place where you can find a lot of mathematicians nowadays, and we are very lucky, communist mathematicians who don't care too much about money, is in France.
I think most of them working for Wall Street.
No more, because many prefer a nice life with time to do science rather than a nice salary. And maybe half of those 10 are still in Paris. Actually, if you go to Paris, the city itself, you'll find as many mathematicians with field medal in one city than in the whole United States. And actually, they are present actually in 2 buildings. So you just need to send a bomb to 2 buildings and you destroy all of them. So this previous toolkit, Scikit-learn, actually is made based on algorithms of one of those mathematicians. Among one of them, one is called Wendelin Werner. He is the first probabilist, specialist of probabilities that was awarded the field medal. And that also recognizes how important probabilities and statistics have become in the field of mathematics. So we called our project Wendelin to pay a tribute to Wendelin Werner. To make a big data system, the next step is a fully distributed storage system. So luckily enough, our company wrote one 6 years ago. It's called NEO, and it's written using the same language as Scikit-learn, Python, using the same data structures, which means we could probably provide natively infinite capacity by using NEO to the data models that Scikit-learn manipulates, then reach some kind of dream for any specialist of machine learning, that is, process volumes of data that go beyond the random access memory capacity. We are going to use the distributed processing system that's in our ERP. It's a kind of MapReduce, but it does more than MapReduce. It's based on ideas of active programming from AppTalk, someone who created that, I think, 25 years ago. He's not known, but what he did is actually more than MapReduce. And then we need a multi-cloud deployment system. That's a bit a buzzword to say. If we have a distributed system, it has to be installed like that, by just one button, automatically on 100 servers, scale up, scale down automatically. There's an open source cloud system called SlapOS that does that for free for 3 years, and that works on bare metal, because we prefer bare metal rather than virtualization to have the best performance. And that makes the stack of Wendelin. SlapOS for automatic deployment and orchestration, ERP5 for distributed processing on Python objects, NEO, which itself is based on MariaDB for distributed storage, and Scikit-learn for machine learning. And that's a quite consistent stack that will be able to do certain things that Hadoop cannot do, for example.
So this is for batch processing?
Real-time or batch, both.
Real-time in terms of second?
Actually, when you do machine learning, the model, you need to produce a model. And producing the model doesn't need and is better not made in real time. But the model itself can be quite small and even be embedded in a device like this one. And that is, training the model doesn't need to be real time. Using the model might be in real time, but can even be embedded in sensors. So for example, in one project we are planning, we are going to put sensors in wind turbines to detect vibrations, then feed with logs a central learning system, then use the model to predict destruction or mechanical failure of the wind turbine. Then this model can be embedded in the vibration sensor itself.
So what is the most complicated machine learning algorithm you have used in training a model?
I know nothing myself about machine learning. The Scikit people know. And the most recent algorithm they use is called stochastic average gradient, partly invented by a person called Francis Bach. So we are planning to use for the wind turbine stochastic average gradient. So that's the user interface, like HTML5, works on mobile tablet and so on. And we plan, of course, to use all the libraries made by the Python community in the world, like Blaze. Blaze is a very nice out-of-core data processing project sponsored by DARPA, or NumPy that provides type inference and just-in-time compilation for Python, or Panda that's used in Wall Street to do things that are similar to OLAP. There is a very rich environment of Python libraries for data processing, half of them being financed by a military budget in the United States. Applications are intrusion detection. I'll give you an example. The nuclear facility in Iran received a virus that was produced partly by Israel, partly by the United States. This virus attacked the control systems, Smets machines, that then gave an order to certain device to rotate faster. By rotating faster, the device broke and the nuclear power plant was destroyed. And then this virus duplicated in 15,000 different facilities in the world, in France, Germany, India, and Indonesia. If one was, for example, monitoring the pressure, temperature, rotation speed of the mechanical machines that are driving the nuclear power plant and comparing the history of these values with history of values learned in the past, it would have been easy to automatically detect a failure and prevent the virus from destroying the power plant. So there are many applications like that, much more interesting than video surveillance or citizen surveillance. Machine surveillance through machine learning has many applications for safety of industry or society. So fraud detection, marketing, media analysis, all these are typical applications of big data. And the business model we plan to implement for Vendelin is a typical German business model. No venture capital, sell our service to companies, make a profit, use the profit to do research and development, and so on. Self-finance, and nearly no marketing. And this way we can guarantee that over the long term, there's no risk of Vendelin being purchased by a company that's going to stop the product. So now I'll try to explain what are the technical challenges we are going to face, and that will take a couple of years to solve. So the first line shows a typical tutorial of using NumPy arrays. First line says, give me an array of shape 2. The second line is an array of, oh, it's a mistake, 2 exabytes of data. So 1 exa lines and 2 columns. And the third line is also 1 exabyte of data made of 1 billion cross 1 billion lines, 1 billion columns. Mathematicians dream of being able to program with arrays like this one. They don't want to think about cutting the array or converting things to JSON, put them in a NoSQL database, put it back. They just want to program, hey, give me a 1 exabyte array and let's process it. That's called out-of-core technology. And sadly, the way to implement it will be different based on the topology of the array one wants to allocate. So, we'll specialize first on a very simple case. Arrays of the second type, like for example 1 billion lines and 2 columns. This is typical of logs that are collected from wind turbines or from nuclear power plants. And how we are going to implement, first we cut the array. We have the array. Then suppose we have 4 independent instances of MariaDB. We are going to cut the array in 12 blobs, then store blob number 1 on MariaDB 1, number 2 on MariaDB 2, and so on. Then the first database will have blob 159, the second MariaDB blob 2610, and etc. So now, that's very usual. And this is what NEO is doing transparently for any Python object. So NEO is a technology that takes any Python object, cuts it into small pieces, distributes the pieces on multiple MariaDB instances, and does that with replication and transactions. So it has 4 components. The top component, the application, is where you run the Python code. Like for every line in the array, x equals x plus line value. The storage component is made of a MariaDB instance with a little layer of Python that implements a protocol to exchange pieces of Python objects between the application and the storage directly. The master component is just an integer generator. Each time you ask something to the master, it's going to give you a new value, like 1, 2, 3, 4, 5, 6. And this value represents the transaction number. So the master actually knows nothing about which data is stored where. It just knows to count, which makes it possible to count very fast and to count a lot. This was actually our trick to increase the bandwidth, increase the number of transactions per second. Our way to achieve that was not to have any central index of data. Then there is an admin service that controls the other services. The reality of the system is that application part will be deployed on multiple servers, storage on multiple servers. There's going to be multiple masters with a master election algorithm. That's how actually we learned that there is no such thing as distributed master election on a non-reliable network, and also multiple admin services. So every part is redundant and is going to work reliably on a local area network. It is not designed for wide area network. Then, in the technology for distributing the storage is super simple. Every object has a unique ID that's called POID. Then we do a hash of POID. For example, 0, 1, 2, 3. Then the hash will tell us which storage to store the object. And there's an indirection that makes it possible to add or remove storages during runtime. So actually, we did this way after reading how a MySQL cluster was implemented. Then we added an indirection so that we could have 24/7 hours operation. So the first version of NEO and the array will be finished within 3 months. It's very easy to implement, but it will not be optimized. We are going to release the first Vendelin developer release in Q3, add a couple of optimization in Q4, and, I should have written Q1 2015, it will be the beginning of real problems to solve. The first one is that we first want to remove communication between the NEO storage and MariaDB through socket. We want direct communication, no socket, and minimize number of copies in RAM. The second problem we have to solve is the problem of,
The MariaDB embed is not a problem. We already have MariaDB as a library.
Yeah, so we have to do it.
But we already have the library.
Yes, I know, but we didn't implement it yet.
Okay, so you guys need to use it.
We need to use it, check it, make sure it really works, and until it really works, we don't know. No, not your part, our part.
So can your distributed array
Sorry?
elements, there are lots of elements.
They are distributed.
In your distributed array. Can those elements be any type of data structure?
The first version we do will be quite specialized for data structures that look like stream or actually no.
It can be anything.
It can be anything. It can be any data structure. It can be distributed in any way. And the way to distribute the data can be programmed by the developer through a meta-object protocol. But the first version we do will only provide out-of-core data, not out-of-core models. And for out-of-core models, and this will be already a huge step for the researchers or for applications. And so the next problem we have to solve, we call it colored caches. It's the fact that in the protocol of NEO, there is a local cache of objects, and we want to be sure that certain objects remain longer than others and are stored in independent caches. Then we'll have to change some implementation of the caching library and code it in C. Then the storage itself is written in Python for now. We are planning to either move to C++ or to Go language. We don't know yet which. And so these are the challenges. Reduce latency. Okay, let's use embedded MariaDB. And it should work. Second problem, we would like not to interpret SQL queries each time.
I mean, for the embedded, prepared statements work very, very good.
So we'll try to use prepared statement. We'll use prepared statement. Then we would like to reduce the number of copies of blobs so that we can take the blob directly from embedded MariaDB and send it to the network.
If it's embedded, we should be able to extend queries that instead of blob, you can have a pointer to a blob. In this case, there will be no copying at all.
Like that, and no
Embedded,
copy.
If not embedded, that's a big help.
But embedded, and we can do. And our storage is already designed as single-threaded on purpose.
So do you plan to support full in-memory?
Sorry? Full in memory.
Yeah.
That's 2016. I'll explain how we plan to do. Then accelerate storage. That's replace Python by either C++ or Go for the storage code. We don't have, some people who like in our company to do C++ because that's known, and others are telling us that Go compiles with GCC and is simpler to maintain over the long term. And optimize cache, that's the idea of colored caching. Then after those issues, the one you said, full in memory of everything, not only the data, but also the model. In Python world, the company that created NumPy now is being financed to create a project called Blaze. And after 1 year and a half, it's still very far from providing the same feature set as NumPy. And it will probably take a couple of more years to cover the feature set of NumPy that is required to run machine learning. So our plan is not to reinvent, it's rather to contribute to that effort by providing a NEO storage to Blaze.
You can bypass it. I understand probably, for certain reasons, especially for design, use purpose, you want to build anything on top of them. But you can bypass that a little. But it takes extra effort, to be honest.
To who? To the programmer?
Yeah, I mean, to implement your in-memory option. There are two options. Build on top of them or just bypass it.
So the approach of build on top of NumPy already exists as it is today, but the code that exists, for example, in Scikit-learn or other places, makes already assumptions of contiguous memory. And so there are many places in the machine learning code that do too many assumptions on the structure of memory, and that's the big issue. And to bypass NumPy, in my opinion, that's what Blaze is doing.
Not 100%. Bypass certain portion.
So this is also an open source project.
Yeah, sure.
So we are very interested in having contributions or help. And I should even say that we have an unlimited budget to hire any number of people. Yeah, because Europe has so much money to spend on research and not people to hire. So if you want to spend a couple of years in Europe, we can organize your visa, everything, like 5 years holiday doing this.
You can do it anyway, in Alaska.
Yes.
You don't need to be in Europe.
Yeah, but I needed to use the budget. But you can go and go back, no problem. And so that's all for today. And I think it's interesting because it shows one possible way, in addition to Hadoop, for doing big data and machine learning based on MariaDB. Thank you.